Hi, everybody. This is section 2.6 in Calculus 3, and the topic of this section is sort of like conic sections in two-dimensional space, but now we talk about surfaces, various surfaces in R3. These are specifically called quadric surfaces, and you can see a new background of this Zoom video. And surprisingly, I found this as a wall in a pretty well-known restaurant in Los Angeles. So even the chefs think that these are pretty cool things to draw. And so we'll get started on surfaces in R3. All right, section 2.6 is about quadric surfaces. Now the word quadric, let me see if I can do this. Quadric is a little deceptive, maybe even misleading because quad means four, right? And here, I mean, you may have studied, surfaces or lines, curves like this. And these are called quadric curves or sometimes quadratic equations because you have twos, right? So x squared, well, that counts for two, and then y squared counts for two more. And so altogether, you can call these something about four, and you can talk about quadratic equations, even though that's technically not quadratic, right? I mean, quadratic equations look like this. Ax squared plus bx plus c is equal to 0. And there's a well-known formula for this. To solve any quadratic equation, you apply a quadratic formula. Okay, but let's not worry about the word quad here, right? We'll be focusing on drawing the geometric things, graphs represented by these. Now, what you can see here is basically involving just x and y, and I hope you recognize these, right? This is really what you studied in Algebra 1 in high school or kindergarten or wherever you learned your Algebra 1. And what are these? These are lines, right? You don't see the z axis, or you don't see z because there is no z on the plane, right? And so what happens is if you extend this and add a few extra things, well, let's first just go without squaring any of these. Okay, what happens if you add a z? Right? This is what we just recently learned in Calculus 3. Anything that has this form, ax plus bx, by plus cz is equal to d, or plus d is equal to 0, whichever. These are also called, well, not lines, but these are called planes, right? But the similarity is there is no curvature here. There's no curvature. Everything is flat, right? And by flat, I mean, there's no curves involved in this. Both are flat objects. This is lines in two-dimensional plane, and this is planes in three-dimensional space. Now, if you square expressions with x and y, but no z, okay, if you square these, x and y, and you can still allow the x term, the y term, and a constant, right? You get something a lot more complicated than lines in R2. What are these? Okay. Well, if one of these is 0, then you get, x squared but no y squared, or y squared but no x squared, and those are parabolas. If a and b are non-zero, then what you get is something called either ellipses or hyperbolas. Right? And so that's, of course, and we'll just review this because you'll be doing a lot of drawings of hyperbolas and ellipses and parabolas in this very section. Right? But now what we'll do is add z to this. So now what are we talking about? You're going to have terms like x squared, y squared, and then you will be allowed to have z squared terms, and then the constants, okay? Or not constants, the first degree terms, the E, F, and then you have, let's see, A, B, C, D, E, F, G, that may be a constant, and then equal to 0. Now, technically, you could also have XY and XZ and YZ, and you'll get what we call a objects of rotated objects. We will not be doing those. We'll be focusing our attention on surfaces of this form. And these are what we will be studying in this section, quadric surfaces. All right, so without further ado, let's focus on this. All right, now the way to do this is actually to draw a bunch of what we call traces, right? And then in order to draw traces, we have to go back to study these, right? So let me just give you a quick review of especially the conics, like the ellipses and hyperbolas, right? So I will call this a quick review. All right, let's see if you can remember how to do this. And should I give you specific numbers? Yeah, I think I will give you specific numbers here. If you have something like this, okay, do you remember how to graph this? Okay, this is something that I hope you studied pretty extensively in places like calculus, pre-calculus. And so look at that, nice curves here, right? And I mean, nice lines. What you want to remember is, and maybe it depends on what kind of a math instructor or professor you had. Hopefully, you studied how this is related to circles. You study things like eccentricity, the directrix, and also major axis and minor axis and so on. But if you study this carefully, I mean, what you get, and you can do even a transformation, and you can let x/3 be your new x, and then y/4 be new y or something. But what you get is an ellipse, right? And in this case, you can, look, I have a little way to make ellipses here. Let's go ahead and do this. This is what you get. Ooh, wow, okay. All right, so what is this? Well, this is an ellipse where the x intercepts are positive and -3, and y-intercepts are +4 and -4. Okay. Now, by the way, this will be written as 9, and this will be written as 16 typically, right? And so this is what you will get. And and again, you can study, things like eccentricity and the foci and so on. We will not worry about the foci or foci or foci, however you want to call this. How do you pronounce this, right? Sounds very much like some doctor's name that is become quite famous, but it's foci, I guess, right? But you don't have to worry about these things in this course. All we have to do for this lesson is to sketch these. Now, what happens if instead of the positive sign, you have a negative sign? Okay, and the point is you can still draw pretty much the same thing. Let's see if I should maybe draw this. Oh, that's not what I wanted to do. Let's see if I can draw this over here. This one will be a little more involved, okay, if you remember how complicated this could be. Right? So what you have is the x and y axes. And then because it's negative, right, this would be the set of, how should I say this, the set of all points such that the difference between distances from point A and point B is constant. And this will be what is called an hyperbola, right? And hyperbolas are much more complicated to draw than an ellipse. Right? In an ellipse, you have these points here, and then you make a sort of elongated circle. So for this one, you do, let's see, this is your x, this is 3 and 4. So the first thing you do is to draw, see here, if I draw the same rectangle, it will be like this, okay? This is actually, what is a 6x8 rectangle around the origin. And this is what you will have also. It's 3, -3, 4, -4. So it's 6x8, right, in terms of the dimensions of the rectangle. And you have an ellipse here. And of course, if you draw an ellipse, it'll be right, here. But that's not the way it works now. If you have a negative sign, then instead you draw these two lines. And I strongly encourage you to draw these lines before you draw the hyperbola, because these are the guiding lines that will tell you where to go, right? And think of the rectangle as sort of an area, like the demilitarized zone or something you cannot enter, all right? So the graph of this hyperbola, the graph of this equation will be in hyperbola. And because x squared comes first, you know, for instance, the point like 3, 0 and negative 3, 0 is on, or does satisfy this equation. So it does go through these points, and hyperbolas, well, it's actually one hyperbola that has two components. Every hyperbola should have two components. And this is one hyperbola, which is a set of two similar or congruent curves, and one goes to the right, one goes to the left, and they approach what we call these asymptotes, okay, which are the diagonals going forever. Now, don't draw like this, okay, because there, you know, I mean, if you were to draw these lines, these will go far away, and if they go far away from the asymptotes, these really aren't asymptotes, so that's no good, okay. All right, just want to make sure. All right, and then one more thing in terms of the review, what happens if these are different? Let's say instead of x squared going first, what happens if y squared comes first? So I switch this. I switch these two terms here. And then what happens here is, let's go ahead and erase this ugly thing here. Right? But sometimes, you know, it's important to point out what not to do, especially for these conic sections. And I have seen many hyperbolas where they don't get closer and closer to the asymptotes. And so I just wanted to point this out. Okay, so now let's draw a, am I in the right mode here? Yeah, okay, let's use red for this. All right, so here, let's go ahead and try this. Now, some of you already know the answer to this, right? I hope many of you do. And then you don't have to watch all the details of this. But you still have 3 square under x and 4 square under y. So the rectangle part will look exactly the same, right? And in fact, the diagonals go through all of these corners, right? The vertices of the rectangle. Remember, I call them guiding rectangles because these are the rectangles. And this is the rectangle that would guide you as you draw your hyperbola. And the fact that y squared comes here first, remember now, points like 3, 0 and negative 3, 0 do not satisfy this, because if you put 3, 0 and negative 3, 0 into this equation, you get negative 1, not positive 1. So in order to get the positive 1 here, you could have points like 0, 4 and 0, negative 4, right? So that tells you that these points are the y intercepts, and there are no x-intercepts, right? And then, of course, the hyperbola still has the same asymptotes as before, and this time it'll be like this. We'll talk about these quite a bit in this section, so stay tuned, right? And just remember how to graph these things. Okay, so now let's move to the surfaces themselves. The first one I'm going to do has nothing to do with this. Well, it has little to do with this. Okay. Number one, spheres. Okay. Now you already know about spheres. Okay. Why do you know about spheres? Well, because spheres are, what is a sphere? Okay. It's a set of all points equidistant from a particular fixed point called the center, right? With the radius r being the distance. And so we have already studied these. And so again, this is a review. And based on the distance formula, it's not 1, it's r squared, right? And so what does it look like? Well, it looks just like the sphere. And when you draw a sphere, I mean, you can do this. Well, of course, that looks like a circle. Well, how do you make it look like, you know, this is actually something in 3 dimensions? Well, you can do this. This is a sort of a cheap way to, well, but very effective way, I think, to make it look like it's a 3-dimensional object. And by the way, when we talk about a sphere, I want you to know, and I hope you already know this, but the sphere is a set of all points equidistant from this point center, right? And then the radius is r. So that means no points inside of this ball or the outside of this ball is a part of the sphere. And in fact, mathematicians, we treat spheres as 2-dimensional objects. even though they sit in three-dimensional space. Why is this two-dimensional? Because if you pick any point locally of this sphere, locally around this, okay, it looks very much like a plane, right? I know there's a curvature involved, it's not flat, but because of that local local property, the spheres are two-dimensional objects. In fact, topologically or mathematically, the spheres are written as S2. We call them two-dimensional spheres, even though they sit in three-dimensional space. All right, so the center here is, of course, x naught, y naught, z naught. You have already completed squares to find these things here. So I'm not going to go over this, right? That's done, all right? No problem here, right? And you have some exercises here in your homework to draw spheres. Now, the next ones are called cylinders. And I'm going to put little quotation marks because they may not look like cylinders for you, all right? And so, for instance, you have, okay, well, here's an example of a cylinder. X squared plus y squared is equal to 4, right? Now you say, well, that's a circle, right? But if you are told this is in R3, then what it is basically a circle of radius 2. And remember, z doesn't happen. That means z is irrelevant. That means any z is fine, okay? So because what we are looking for is a set of all points x, y, z such that this is true for that point, okay? Remember that whole idea of joining an exclusive club? If you're an x, y, z and you walk into this space and you say, I want to be a part of the cylinder, they'll ask you, what is your x, y, and z? And the first, middle, and your last name. And if you say, well, I am 220, then you'll say, congratulations. No, you can't, all right? 200, okay, yes, you are a part of this cylinder, okay? 020 is okay. 027 is okay too, because it does satisfy this equation, right? So the whole point, the set of all the points satisfying this will be a cylinder, okay? No problem here. But in the definition of the new definition or our definition of a cylinder is any curve that gets extended in a direction, or maybe I should say in the what's going on here, in the direction of an axis. Okay, so so for instance, you could have something like this, and let's say you have a sine curve. Okay, that's a sine curve. And what is this sine curve here? This is a sine curve that looks like z is equal to sine of x. Actually, it looks like negative, huh? Okay, yeah, sine of negative sine. Z is negative sine x because as x goes this way, right? It goes down here first and up here, down here, right? So what does this look like in R3? If you are given this equation, z is equal to negative sine x in R3, you see x and z, but no y, right? Well, that means y is irrelevant, and that means you just extend this in all y directions. So what does this one look like? Well, the surface is going to look, well, it looks ugly here. It looks like this. And you extend it in the y direction, so there will be a whole bunch of lines parallel to y. So this would be like a wavy piece of paper or a corrugated piece of paper or something, right? So this will be a wavy surface, but it looks exactly the same no matter what y value you cut this at. Make sense? Right. So all of these are called surfaces, even though, we think of, called cylinders, even though for us, typically in the real world, cylinders seem to have to involve a circle, okay? But these are all cylinders. Okay, so here's another example of a cylinder. X squared plus y is equal to 0. Let's try to graph this. What does it look like? Remember, no z. Z is missing, and that means it is it gets extended in the z direction, right? So let's try to graph this. All right, and can you graph, well, you know, y is equal to x squared, right? So this is x, this is y, remember? And so your graph, and you can just assume first that z is equal to 0. And your parabola should look like this. You see that? And so what I'm doing here is I'm imagining there's a floor, a canvas, what I call, and our canvas here is when z is equal to 0. Okay, imagine a big sheet of paper, basically your floor, and you're drawing this equation y is equal to x squared on that floor. Okay, that would be kind of fun thing to imagine, huh? You're on the floor, in your house, and you have this red marker and you're drawing a parabola on your floor. I hope your mom or wife doesn't live with you because they probably wouldn't like that. All right, but anyway, this is, you know, this is what the parabola looks like on the floor of x is equal to 0. Now, because there is no 0, no z in here, you just get to extend this, right? So this will be the set of all points satisfying this equation regardless of z, right? So this is what we call a parabolic cylinder. Not a circle. Oh yeah, so the first one I drew is called a circular cylinder. You know, because it's basically a circle extended in the z direction. This time it's a parabolic cylinder because it's a parabola extended in all directions. All right, so what you do here is to draw the curve and extend it or stretch it in the direction of the missing variable, okay? So the key here is to draw your curve and stretch or extend in the direction of what? Of that missing variable. All right, and that's how you do graph these surfaces, right? And these are all called cylinders. Basically, a cylinder, and maybe I should just mention this too. A cylinder means one variable is missing. And every time you see a one variable missing, whether it's x, y, or z, you will have a cylinder because that means it's basically a curve extended or stretched in the direction of the missing variable. All right, we okay with this? All right, now I'm going to write the next one and I'm going to make this blank, all right? And I want you to figure out what happens here and I'll write down the equation. This is fun, okay? I'm going to just write this and then tell you what happens with what we call traces, okay? And when I say traces or draw a trace, that means we let one of these things equal to 0, okay? So I want you to graph this, assuming x is equal to 0, y is equal to 0, and z is equal to 0 in their respective canvases, right? And so let me tell you what I mean by this canvas, or basically these are coordinate planes. Okay, so very quickly, and I'll let you figure this out on your own, but when I say x is equal to 0, I'm talking about this plane, right? So think of this as a canvas or the wall on which you draw this equation, or you figure out what this equation is when x is equal to 0. Okay, so that means this part will disappear, and you can probably see what the other thing is with y and z, right? And then for y is equal to 0, that means where is y equal to 0? Okay, so the xz plane, that's this. This is your canvas on which you draw all the points satisfying this equation when y is equal to 0. Okay, and finally, when x is equal to 0, that means you're on xy plane. On your floor, you graph what this equation is like when z is equal to 0. These will give you the 3 traces, what is known as the traces, and they will help you figure out what that object is. So go ahead and try this, and then maybe you can describe what you come up with in terms of these traces, put them together, okay, eventually, and then you tell me what kind of a surface you get. That is your first assignment. I'm going to stop this, and then I'm going to go into part 2 after this.